Hey, what's up everybody? In this video, we're going to talk about predicting solubility and how to do it and how to make those predictions, also explaining why. Specifically, we're going to try to answer the question, will CCl4 be soluble in water? To do that, to answer that question and make that prediction, we're going to be walking through a series of steps summarized in these gray boxes. You can apply this exact same process to really any set of substances you're asked about. Let's get started by first making sure you know what is the solute and what is the solvent. The way that this is worded here with CCl4 in water, that is implying that the CCl4 is dissolving in the water, which of course means that H2O is the solvent, so I'm going to keep track of that beneath the solvent column, which of course means that the CCl4 is the solute. Now that I know what is what, I can start to describe the types of particles that make up these substances. Are they molecules? Are they ions? What are we dealing with here? In each of these examples, we have nonmetals bonded together, right? Carbon is a nonmetal, chlorine is a nonmetal, same thing with hydrogen and oxygen. And in almost all cases, when you've got nonmetals bonded together, we're talking about molecules. So as far as particle type goes, we're gonna clarify what each of these things are, right? CCl4 is made of molecules, and so are the waters. There's one other component to this though. Anytime your particle type is a molecule, you're also going to want to clarify what type of molecule in terms of polarity. So are these polar molecules or are these non-polar molecules? To do that, you have to draw out the Lewis structure of each thing, check the shapes of those molecules, and look for things like electronegativity difference and symmetry. Here, because this is a totally symmetrical arrangement of the chlorine atoms, we can say, really without much extra work, that CCl4 is specifically a non-polar molecule, whereas if you draw out the Lewis structure for water, it's got giant electronegativity differences between O and H, and it's bent in shape, so it is asymmetrical. And that means that water is a very different type of molecule because it is polar. Okay, so the next thing you want to make sure you know is what are the solute-solute interactions. In other words, if you have one CCl4 molecule, sometimes it helps to draw this out just to get a good visual. If you've got one CCl4 molecule next to another CCl4 molecule, how are they interacting with each other? What forces of attraction exist between those two things? Since they're both non-polar, that means there's only one way that non-polar molecules can interact, and it's called London dispersion forces, and we'll abbreviate that LDF and say that CCl4 molecules will interact via LDFs only. If you do the same thing for water molecules, again, here's a second H2O. We're trying to consider what is the attractive force that would be formed between those guys. Because they're both polar, that means water molecules are going to experience what we call dipole-dipole forces. In particular, water molecules are going to experience an extra special strong type of dipole-dipole force called a hydrogen bond. You could also mention London dispersion forces here because all molecules will experience those LDFs, but they're really not going to play a role because hydrogen bonds are so much stronger than these likely weaker LDFs. Okay, at this point in the process, I can actually jump all the way down to the end and make my prediction about solubility. We're not going to be able to fully explain why yet, but at least we can come up with an initial answer. And we can do that because if you look at the top of the video screen, there's this statement in green, and I'm going to read that just so we're clear on what's happening. A solute, or when a solute has similar types of interparticle forces to the solvent, it will be soluble. And since I know what those interparticle forces are, right, we just wrote them out in that lighter blue color, that allows me to say whether CCl4 is going to be soluble or not. Because CCl4 has London dispersion forces only, whereas water has a very different type of interparticle force, hydrogen bonds, and because they are not similar, my prediction will be that they are not soluble in one another, or CCl4 will not dissolve in water. So that's the prediction part of it. It's not the why though, and that's another element of this. To fully answer why, you've got to make one more consideration, and that's the only thing we haven't addressed in my series of gray boxes here, and that has to do with the solute solute-solvent interactions. The most important part, arguably, of the whole process. Here's what that means. Again, I'm going to draw these molecules out to give us the visual. What you're essentially doing here is saying if a solution was to form, so if CCl4 molecules and water molecules, or if CCl4 did dissolve in water, we're trying to say what type of interactive force would occur between those two separate things. How would the CCl4s be attracted to the waters? Since we know that CCl4 is nonpolar and water is polar, there's really only one type of interactive force that can form between these two substances, and it's called a dipole-induced dipole force. The water is the dipole, and we're going to induce a dipole on this nonpolar thing. So let's just list those out in the official place here underneath solute-solvent interactions. Okay, so now that we know the name of the force that's going to be formed between those two molecules, what does this do for me? You've got to know one more thing, and that is dipole-induced dipole forces are also a particularly weak type of attractive force. So just keep that in mind, because in a second we're going to compare it to what holds water molecules together, hydrogen bonds, which are particularly strong. We're going to come back up to the top of the screen one more time, but this time look at the statement in red, which tells us in some cases the solute-solvent interactions are significantly weaker than the solute-solute, which is not the case here because my solute-solutes are LDFs, also probably fairly weak, but weaker than the solute-solute and the solvent-solvent, and that's what's true in this case, because my solvent-solvent interactions are hydrogen bonds, which are going to be much stronger than these weak dipole-induced dipoles. And this statement tells us that when that is true, a solution will not form. This is going to allow me to explain why carbon tetrachloride and water do not mix. So we can say that the dipole-induced dipole forces, which I'm going to abbreviate here, you would say that they are too weak to overcome. That's the typical wording you would see in an explanation like this, to overcome the strong hydrogen bonds between water molecules. Alright, so just to wrap it up, we have predicted that it's not soluble, and we know the reason why is because the solute-solvent interactions are too weak to overcome the hydrogen bonds between water. That also wraps it up for this video. Thanks a lot for watching.